Hello, class. For your lab activity number 4, solving system of linear algebraic equations, you have to make a program that finds a solution to a system of linear algebraic equations. Inputs will be the coefficient matrix, the constant vector, and the tolerance in percent. This you need for iterative methods. Output will be table showing iteration number, the root or solution estimates. That's from x sub 1 to x sub n and approximate percent relative error EA1, EA2 until EAN. Files to submit will be Matlab programmer programs. Depends on you if usahon na ba ninyo or modular inyo pagka-implement. Then lab report and the folder containing these two. File name format, group number underscore course code underscore section underscore lab activity number. So for your lab report, it will be like this as a sample, and folder name also like this. But for your Matlab script, it depends on you how you will name your Matlab script. And third thing to do in your lab activity 4 is to evaluate the other groups. So every group is required to evaluate other groups. Let's now see how those methods that we discussed in lecture 6 are implemented in Matlab. Kini po ay. For your Matlab script, also include this one, your group number, then the name of the members. It's also a good practice that you write a description of your program. Let's try this. Okay, so it's asking for the coefficient matrix. For the matrix, as described here, for a system of linear algebraic equations, in this form, a11 x1 and a1n xn equal to b1, then an1 x1 until an and xn equal to bn. So if this is the form of your linear algebraic equation, then the coefficient matrix will be like this, a11 space a12 until a1n. So para ano nila, para ano nga first row sa imong equation. Then kung sa ato na ka sa second equation, or that's the second row, gamit ka og semicolon. Then a21 space a22. So in between sa mga elements sa same row, space. Pero kung in between sa rows, semicolon ang gamitan. Then for constant vector, b1 semicolon b2 until bn. So it's asking for a coefficient matrix. Let's try this one. This we already solved in our lecture video, but just to confirm. So coefficient constant vector is, so we are not to choose. Let's try first Gauss elimination. So that's it. The same answer with the lecture in our lecture videos, 3, negative 2.5, and 7. Let's try another. Let's try this one. So it has successfully given us the solution. Another. This is just the same set of equations, but just rearranged. Try na to. So see, not a number. It returns not a number. So why is that so? As mentioned in lecture 6.1 and lecture 6.2, Gauss elimination has a deficiency that is, um, in particular, the naive Gauss elimination. So it can't determine whether there's a division by zero, and it's possible that there's a division by zero. So if you are to look at the coefficient that we use, this one, so A1, the diagonal elements, 225, 175, 225, A22 is 175, A33 is 275, A44 is 275. So the diagonal elements are non-zero. Hence, it gives us the answer. However, if we rearrange that such that the diagonal elements, though the same set of equations, but the diagonal elements, na 0, A11 is 0, and A22 is 0, um, diba? It will now, there's now the division by 0. So that's why it returns not a number. Okay, so this is the an illustration of naive Gauss elimination. So for this, in order to address this deficiency of naive Gauss elimination, we need to employ partial pivoting. So if I'll try to do that, so I'm using partial pivoting immediately after the first loop. So let's try that. So see, though the diagonal elements in the original matrix given by the user is not has 0 diagonal elements, but still it was able to give us the right answer. Okay, that's because of partial pivoting. So it means within the program was able to rearrange into interchange the rows so that the diagonal elements are non-zero. Now let's try Gauss-Seidel. Let's try this first. Still the same on the same yes, the same problem in our lecture video. So after 4 iterations, all root estimates are within the tolerance. Okay. So as you can see, though X3 at third iteration is already less than 0.01, but the other two are still above 0.01. So that's why the program has to iterate again. Now, let's try another. Same set of equations, but just rearranged. So, as you can see, Gauss-Seidel diverges. Oh, negative 193, then positive 4.1029 times 10 to the 5, then negative. Then, as you can see, nagkadako siya. No? Small paghihapon sa X2 and X3. Nagkadako. Antod nga, infinity na gyud. Okay. Ito, paning diverge. But why is this so? Did you remember what I said in the lecture video? The necessary condition for Gauss-Seidel to converge is that the system has to be diagonally dominant. Diba? So for this one, A11 is 0.1, and that's less than the sum of the other two. A22 is negative 0.1, so the magnitude is 0.1, and still less than 3 plus 0.2. A33, yes, it's greater than the 2, but all in all, this matrix is not diagonally dominant. And as mentioned in the lecture video, the necessary condition for convergence for Gauss-Seidel is it has to be diagonally dominant. So if you are to check the previous matrix, this one, this is diagonally dominant. 3, A11 is 3, A22 is 7, also greater than the other two, and A33 is 10. So really diagonally dominant. So that's why Gauss-Seidel was able to solve this, to arrive, to converge. Okay, so let's try Jacobi. So after 5 iterations, Jacobi is able to arrive at the solution. Okay. For Gauss-Seidel, it's just it only took 4 iterations, but for Jacobi, 5 iterations. But still, successfully happened. Then, as you can also notice, they have different values. Okay, for during the iteration first, second, third iteration. That's because wala man nag-up, the updated value is not immediately used. Okay, as compared to Gauss-Seidel. For example, it's 2.6167. Then this one is 7.14. Negative 2.7571. If you are to check with Gauss-Seidel, it's Gauss-Seidel, this one. Negative 7 point, it was 7.14, pero dari kay 7.0056. It's 2.9906, but Jacobi, it's 3.008. So it's because it's not using immediately the updated values. Now let's try katong delete diagonally dominant. Gaya eh. Open 01. So still, the solution diverges. Jacobi diverges. Again, the necessary condition for convergence is that the system has to be diagonally dominant. Ato ang sa pamanggong pag-program akong giset ang maximum iteration to 100 iterations. After 100, yung exit na din sa program. Sumotong direct. Nasa Gauss-Seidel kanina. Yung to infinity. Okay, so but the point here is the necessary condition for convergence is diagonal dominance. And what are there else? Oh, that's it. Thank you for listening.